All right. Sorry for the delay. My name remains Maksim Panchenko. I'm still planning to talk about BOLT and how we applying it to the kernel, trying to apply. It's an ongoing work. It's been fun, but I hope I can share it with you. And let's get rolling. Hopefully, we'll have a few minutes for questions after this. We'll start with the overview. Why the hell we want to optimize kernel? Like, why does it need more optimization? But most of the talk will be about the challenges. Like, why is it so difficult, so hard? Of course, I'll share the progress and the plans. So, Linux kernel, right? It lives at the bottom of the software stack. You have hardware. You run kernel with its drivers before you actually run applications. And Linux is probably like the most ubiquitous piece of software in the world, right? It runs on a lot of embedded devices, on cell phones, on servers. We're right now targeting just servers, just at x86. But as you imagine, it's definitely an interest in optimizing the kernel for, and when I say optimizing, like in my mind, it's always for speed, but for other people, it will be like for size, right? For embedded. But since we're talking about the servers, yeah, it's mostly speed. And when we look at the system as a whole, right? Let's say you're running something in the data center, and you want to optimize your web server, and you're spending, you run profile and see where the cycles went. And mostly people look at the application itself, right? They don't look at the kernel because it's given to you. But apparently, there's a lot of opportunities to speed up your application by speeding up the kernel. And you wouldn't imagine that because we have like thousands of engineers around the world like hacking performance improvements into the kernel itself. At the same time, you wouldn't believe it, but they were not using PGO like till a couple years ago, and like Clang was adopted by Google. Like a lot of work went into like making Clang work with Linux kernel, and they switched on the PGO, and it was like drastic improvement, and not just for one application, right? As you can imagine, it speeds up like whatever you're running on top. So if you run, or at Meta, if you run, let's say, web service, it becomes faster. If you run database runs faster. So there's a lot of opportunities there. But there's still more on the table, like LTO, for some reason is not being used. I think there might be some correctness issues, but this is not the topic of this talk. We'll be focusing on BOLT. So the quick overview, like why you want to use BOLT, but before why, let's say what is it, right? Well, we take the application that runs in the data center collect profile, and we rebuild this application. When I say rebuild, we don't recompile it. We actually take the binary, break it, and like relink it internally, which is a fast process. And we use the most accurate profile information. You can kind of do the same in the compiler, but you need probably 2 profiling passes to get kind of parity with BOLT. And then you wouldn't get exposed to assembly code, which is important for Linux kernel. And when we try to run the kernel, but when we collect profile on the kernel and loaded it in BOLT, we produce the stats, the dyna stats that describe the opportunities, what will happen to the binary once we optimize it. So for example, if we say the branch is only taking one direction, right, we will change it or put it in the most optimal way. And apparently, there's still a lot of opportunities. So if you can see the dyna stats there, the taken branches were reduced by 56%. So it gives you an indication. It doesn't tell you exactly by how much faster your application will run, but it gives you like a good signal that after applying Bolt, it will be faster. So with this in mind, we decided, yeah, let's proceed. Let's see if we can improve the kernel. We also measured iCache miss ratio on the system, and it turned out to be quite high, which again indicates a good opportunity for Bolt. If you're familiar with recent Spectre meltdown, you know probably that Linux kernel and some other applications, they implement the red line mitigation, which is a huge performance penalty if you have a lot of indirect calls. But in Bolt, we can do indirect call promotion, replacing for the most frequent targets the indirect call with direct one, in which case you don't need the red line. So that's another opportunity. The question is probably the most frequent question. So I'll address it before we go to Q&A. Like, do you need a special kernel like for every service? Let's say you optimize for network, you optimize for databases, for web. Will you have different profiles and you'll need like 3 different flavors of the kernel for that? And it turns out that not really, unless you going after like every single bit of performance. If you combine the profile, let's say you collect it for 3 different services and combine the profile, it will be good enough in a sense that most of the benefits you'll get from this profile, I would say 95%. There's a paper I'm going to reference later in this presentation that actually goes into detail. They actually did the comparison. Of course, it may vary, right? Like in your scenario, which I have no idea like what you'll be running. It may be like a special case, right? And well, if that happens, it happens. Like you will have to collect the profile. Again, the beauty of Bolt is that you can run it really quickly. So in theory, as you run the application, you can collect profile, and after some time, you decide, okay, I'm going to need to reboot for whatever reason. And before the reboot or right after, well, probably before the reboot, you can actually take this profile and apply Bolt to your Linux kernel. It will take probably like 10 seconds. Yeah, it's that fast because kernel, it's relatively large, 16 megabytes of code, but it's not like large binaries that are like 500 megs of code. So once you do that, you reboot the machine, it runs faster. And this reminds me of like Windows systems from the 90s, right? When it's things are getting slow, you reboot it, they run faster. But here, they actually, they can all run normally, but after reboot, they run even faster. So that's the idea. So why is it so difficult to apply Bolt? We've been running Bolt on many large binaries, and this is just like another ELF or ELF-ish kind of binary. It's not. It differs from regular ELF in many regards. But why is it difficult to apply any binary optimization? Why haven't people done it before? And I looked into the existing research. I couldn't find at least any open source project that successfully optimized or binary optimized the Linux kernel. So, and there are multiple reasons, which I will describe. There's cold volatility issue. There's like the ELF structure of the kernel has its peculiarities. As you can imagine, like testing is not simple, right? It's if the application crashes, not a big deal. You like get the core dump, like restart it, fix the problem. Gets more complicated with the kernel, and related is debugging headaches. So what does it mean like dealing with code volatility? It's if you take a tool, a disassembler, let's say ObjDump on Linux, and you look at the kernel, you think you see the code that will be running, but it's not the case. There are several modifications the kernel does to itself. And it does them during boot time, like part is done during boot time. For example, it detects it's running on Intel versus AMD. It's going to change some instructions, like in the code, depending on the features that are enabled. And for ftrace utility, it will patch other instructions. It also has a special optimization mechanism called static keys and static calls that will patch branches depending on conditions of some global variables. And I will go into detail. I think this is quite interesting, like for me as a compile engineer, like to look into that. So let's look deeper into static keys. So that's a dump from Bolt. So you see a basic block with one successor, right? So it ends with a jump, but right before this jump, you see like a knob with, interestingly, with a size 5. And if you don't know anything else and collect a profile with last branch records, Intel feature, you will see that the branch is taken starting from this knob, and it doesn't make any sense, right? If you're not familiar with static keys, what happens at runtime? Not always, but sometimes, kernel will patch this instruction, and the knob becomes jump. That's why it was 5 bytes, right? So the long jump on x86, and it has like a different destination. Obviously. Now you don't know like what is the success of this basic block. Is this this label or that label? So how do we represent these static keys? The static keys, the idea behind them is when you have the global variable that almost never changes or changes like every few minutes, and you check it in many places. You don't want to do this, right? You want to eliminate this check. This is what they do with inline assembly. So they, like most of the time, the instruction is not, right? You're not doing extra work. But then when you change this global variable with a special call, the helper function will go through all locations that reference this key and convert this knob to jump, or vice versa. So in the source code, it's represented kind of like a conditional jump. And this is basically what it is. And this is how we're going to add the support in Bolt. And the records for every location in the code, every record includes like the jump or knob address, the target address where the jump is going to go, and the associated global key. So how are we going to do this in Bolt, or how we already added it? So we see this knob or jump, and as I mentioned, it's actually a conditional jump. We just need the special conditional code for this, right? So there are a bunch already existing, and luckily for us, in LLVM, MC instruction is represented with conditional code is just extra operand. So if we extend this operand, like from the existing, for like 16 enums, we can actually get the new conditional code that we can use in Bolt internally. Of course, hardware will not understand it. We don't need to create encoding for it, but we can indicate it in the code, right? So since it's happening in runtime, I decided to use like IT for it. So it's kind of like JIT, jump to this label, which can be either taken or not. And with annotations for Bolt IR, we attach more information there, right? So basically, how the support is implemented, we disassemble functions, we detect the static keys, we convert jump/knobs into these conditional jumps, and we build CFG with this information. Now the LBRs actually can be attributed correctly. We can do all optimizations, and we just have to be careful during code emission or before code emission to convert them back and update the records. Static keys are used for probably 20% of the hottest functions in Linux kernel, so they're quite ubiquitous. I mentioned they use 5-byte knobs, but they don't always have to be 5-byte knobs. We have shorter jumps that we can potentially utilize, so there's opportunity there. I've seen cases where statically the branch was marked predicted the wrong way. Of course, developers, they cannot know what's happening in production, so this is where Bolt can help. Similar to static keys, another mechanism implemented is called static calls, where indirect calls are being replaced at runtime with the destination. So instead of having the indirect call, you can change the target of the call, or sometimes you can revert it to node. So we have probably, there's still maybe 5 more minutes for the talk. For Q&A, and 5 minutes for Q&A. That sounds good? Yeah, okay. Yeah, because I have a couple more slides. As I mentioned, there's like alternative instruction sequence. I don't have time to go into details, but yeah, you can have actually not just jumps replaced, but the whole sequence of instructions with the new sequence. So kernel is quite smart about it. It can do like knob optimization when it has to pad with knobs. It can replace branch targets. So this is a little bit trickier to support than static keys, but we can, at the start, we can ignore these functions, and they are not as frequent as the one with static keys. Probably just a few percent of all code has alternative instructions. There are a bunch of others. Para instructions, there are SMP logs that are not important on like multi-core systems. But the beautiful thing is that we have a way to detect all the mechanism that we don't understand, because we ask the linker to save relocations for us. So if something references code in the middle of the function and we don't know what it is, it's probably the safest not to touch this function. And Bolt can do this, ignore this function, but optimize the rest. Which brings me to the topic of how we update ELV. And for normal file, right, for normal application, we will rewrite the code. We will create a new segment and emit all new code there. It's more difficult with the kernel. So what we're sticking to right now is what I call incremental rewriting. So we rewrite functions in place, and we try to take like slow steps. So you wouldn't get all the gains, but at least you make the progress, right? As you do the development, you can already use it and already gain some benefits, although not full. But of course, at the end, the goal is to achieve like 100% coverage. Debugging is, as I mentioned, tricky. There are some kernel panics, which are actually easy to track. Because the kernel panics, it gives you the stack. You can actually see the location, and in my experience, you can figure out like what's happening in a matter of minutes. It's not a big deal. Much worse is when the kernel is stuck, especially during boot. It's like it's not doing anything. You have no idea like what did I do that made it feel that bad. And in one case, I tried to narrow down what function was changed. And I went to the last function and said, yeah, this must be one. And I disabled this function, and it still was not cooperating. It turned out that I changed the data that was not even allocatable. It was just a record for the section, for the ELV section. Typically, it doesn't matter, right? This part is not loaded into the memory, but I think somewhere in the kernel like distribution process, this data was used, and also the peculiar data, the case is that it was located at at address 0, and it was in the middle of the segment. So I had to fix this. So the progress we made, it's first booting in the VM was already like a big success, but then we booted on hardware, and right now we're actually starting to test in production and doing performance measurements. As I mentioned, it's a gradual increase of the coverage, so I don't expect like full performance benefits from the start, but in a few months we should get where we want to be. All right, I think that's the end of the talk. I ran out of time, so thank you for your patience. I know we have like
for questions.
Yeah.
Yeah. Hello. Nice talk. By the way, very nice talk. I'm curious as to what was the procedure that you used to profile the kernel? Did you use user mode Linux? Was it in a QEMU instance or?
Oh, you can use perf to profile the running system.
Perf on user mode Linux.
On the yeah.
Or did you run the kernel on bare metal?
On the bare metal, yeah. On the bare metal with perf, you get all the LBR records. That's not an issue. Probably an issue in the cloud, but once you have access to the hardware, yeah, it's not a problem.
Okay, thanks.
Surprisingly, yeah. Luckily for us, yeah.
Thank you.
Do we have
Let's have a round of applause.
All right. Well, I'll be happy to take questions. I'll be still here.